Okay, so here's where we were last time. We were talking about this idea of diagonalization. So let me just remind you what diagonalization is. It's a concept that comes in stages. We have to define little bits at a time. First, this idea of similarity. What does it mean for two matrices to be similar? Well, similarity is defined in terms of a conjugation relationship. It's a very algebraic statement, but really the better way to think about similarity, or at least the more intuitive, in my opinion, way to think about similarity, is that we're talking about change of basis. Right? So a similarity, two matrices are similar if ultimately they represent the same thing. They both represent the same linear transformation, just kind of in different languages, one with respect to one basis, the other with respect to a different basis. Okay. All right. We can then talk about what it means for a matrix to be diagonalizable. Diagonalizability is defined in terms of similarity, but let's think of that from a change of basis point of view, just like we did last time. Diagonalizable means that a matrix is similar to a diagonal matrix. Okay, said differently, that a matrix represents a linear transformation, and that linear transformation is really diagonal. If you write down to it, that this linear transformation should be thought of with respect to a different basis. The linear transformation should be thought of in a different way, in a different language, in which it is diagonal. Right? So I like to think anyway of diagonalizability of a matrix as basically saying, look, this matrix is representing something that's much simpler than the way you're representing it. You're looking at your matrix with respect to the wrong basis. If you were to just think about your linear transformation with respect to a more clever basis, this linear transformation could be represented really easily. This linear transformation could be represented with respect to a diagonal matrix. And that's what we mean by a diagonalizable. Okay, so simply by changing your perspective, you can make it diagonal. Okay, all right, and then reminder. There's this discussion of this language. I think this is confusing, but when you talk about putting a matrix into a form, this used to bug me. If you are changing it, in what sense are you putting it into a form? Aren't you just making it a different thing? So it's not it anymore. So what do we mean putting it into a form? It seems kind of contradictory. So the way I want you all to think about that is, as we were discussing last time, that really there is an underlying thing that we're ultimately interested in. When we were talking about row reduction, what we were really interested in is the underlying solution set. The matrix that was given, the A or whatever that was given, that was clearly an awkward way to describe what we're really interested in, namely the solution set. So all we're doing when we do row operations, multiplying by elementary matrices, however you want to think about it, is we're talking about that same solution set, just in a different way, and representing it hopefully with respect to by way of a matrix that's that makes it easier to understand. Right? Likewise, when we're talking about diagonalization, what we care about is the underlying linear transformation. So make sure to keep that in mind. We are not talking about homogeneous solutions, right? And really, when we write down a matrix, the matrix isn't really what we're fundamentally interested in this context. What we're really interested in is that underlying linear transformation. This process of doing conjugations, or to say it a little differently, a little bit more intuitively, this process of doing change of basis, the whole point of that is that it does not change what we are in fact really interested in, the underlying linear transformation. And so this process of doing conjugations and change of basis to get into diagonal form is just so that we can understand what we really care about in a more convenient way. We're not really changing the thing that we're interested in. Okay. All right, so there was a lot of discussion on that last time. Okay, so now we're going to get our hands dirty. Let's try to do one. Notice in all of this discussion, there's no indication of what basis should I pick, right? Exactly what conjugation should I do? How precisely do we actually take a linear transformation and represent it with a diagonal matrix? So we're going to just take a whack at it here and see what happens. Let's try this. Here's a matrix. Y'all will recognize that matrix. We've already played with this significantly. We already know the eigenvectors and the eigenvalues. Here they are. There's the eigenvalues. There's the eigenvectors. Okay. So let's take that matrix. Keep in mind this matrix represents some linear transformation. That linear transformation is what we're really interested in. Get right down to it. I want to understand that linear transformation in a different way. I'm going to try to represent this linear transformation now with respect to a different basis. And I'm going to pick here, just to see what happens, a basis made up of our eigenvectors for no particularly obvious, immediately obvious reason. And it's kind of a weird thing to want to do. I mean, eigenvectors was section 5.4. Change of basis was section 5.3. Right? There was no obvious connection to change of basis when we were talking about eigenvectors. So, not clear why we'd want to do this, but hey, let's play the game. See what happens, just for fun. Here we go. Do keep in mind that when we do this change of basis, when we're going to rewrite in terms of this new basis, this new matrix, we compute it one column at a time. And remember, we have a formula for how to compute the columns. You take the input basis vectors, and you do the linear transformation to them, and you write the results in terms of the output basis. Right, so what we have here is explicitly our formula for finding the columns of this matrix. This is a very plug-and-chug calculation. Here we go. What is T of V1? Good news. V1's an eigenvector. T of V1 is really easy to calculate. It's just -1 times V1. So because it is an eigenvector, it's easy to compute its image. T of V1 is -1 times V1. Okay, that was the first part of the process. Okay, next, how do I write -V1 in coordinates with respect to the script V basis? Well, here's our usual predicament. We've got to figure out how do I write this vector, -V1, how do I write that as a linear combination of these basis vectors? So it's something V1 plus something V2. And notice that this little puzzle that we have before us is one of the freebies. This is one of the easy ones. We're trying to write a multiple of a certain vector as a linear combination of a list that includes that vector. So you write down the obvious solution. What we have here is -1, I'll do this in coordinates, -1 V1 plus 0 V2. So those coordinates are -1, 0. All right, so there's our first column. Fine. Okay, second column. Plug in the second basis vector. That second basis vector, eigenvector, again, now that was on purpose, right? I deliberately picked them to be eigenvectors, so we're again get to capitalize, and T of V2 is, well, 4V2. Okay, next, how do I write 4V2 in terms of V1 and V2? Well, same game, same lucky break, 0, 4. Everybody see what happened there? And now keep in mind that's the columns of the matrix that we're trying to compute. And so therefore, this is the first column and this is the second column. And there's our matrix. And lo and behold, diagonal matrix. So we have successfully diagonalized that original matrix up here. Successfully diagonalized it. There is its diagonal form. So this diagonal matrix represents the exact same linear transformation as the original matrix A. It's just representing it with respect to a different basis. Everybody okay? Questions? Okay. All right, now how did this happen? Is it the fact that I picked eigenvectors? Is that what made this work? And I'm going to give you 3 perspectives on why the answer to that question is yes. One is I'm just going to kind of trace through this calculation and try to do a hand-wavy sort of can't you see kind of argument. And then I'm going to give you 2 different proofs that take 2 different points of view that have 2 different sets of merits that I think both of which I think are nice. So first of all, let's just trace through the calculation. Let's look at this kind of one column at a time. I mean, looking at this first column. What is it about that first column that exhibits the diagonality of this matrix? Well, the diagonality comes from the fact that this is a 0 right here. As far as the first column is concerned, the fact that that's a 0 is what makes this diagonal. So the fact that that's a 0. How does that show up over here? Well, that second 0, all that is just that as a consequence of the fact that this is a multiple of V1 only, no V2s. And why is this a multiple of V1 only? Because V1 is an eigenvector. That's why. So you can really directly trace it back. From the point of view of the first column, that 0 is what matters. That 0 means there's no V2s. That means it's all V1s. The image of V1 is a multiple of V1. Okay. And likewise for the second column, let's trace that one back. Looking at this second column, that 0, the fact that I have a 0 there is what, as far as the second column is concerned, makes this diagonal. That 0 is there. That 0 tells you how many V1s are in there. So the fact that there are no V1s in T of V2, the fact then that T of V2 is just a multiple of V2, which is then the fact that V2 is an eigenvector. So now this is just kind of a algebraic, numerical, you might say, sort of appeal, but I think you can kind of see how this is sort of how it ought to work. And this pretty persuasive, just from a hands dirty point of view. Let me take a pause on this real quick before I go on. Any questions? Yes.
So if you have the eigenvalues and eigenvectors, your change would always just be that matrix of your eigenvalues.
Yeah. I'm gonna. There's a summary that I've got down below here that. But pretty much yes, just what you said. Did I see another hand over somewhere? Yeah.
So by choosing the basis to be the eigenvectors, are we still at the moment just designing this so that we get the diagonal?
Oh yeah. I deliberately. This is an attempt where I've deliberately attempted the right way. That's right. Yeah. Yeah. And this is always going to work, as it turns out. Let me rephrase that. This strategy of choosing a basis consisting entirely of eigenvectors, when you can do this, this always works.
So we haven't made it clear why we do that.
Well, our goal is to diagonalize. What we have not made clear is why we care about diagonalizing. The biggest persuasive answer that I give you is why we would like to diagonalize, aside from, trust me, it's going to be super convenient when we're solving differential equations, is diagonal matrices are kind of simple, right? They're chock full of zeros. I love zeros. Zeros represent stuff I don't have to worry about, right? So diagonal matrices are, you sort of expect them to be nice. I'm going to show you a couple of simple examples later today as to why we like diagonal matrices and why we like to diagonalize matrices. But the big application is going to be in chapter 6. Yeah. Yes.
You said that's for certain matrices there aren't as many eigenvectors.
Yeah, that's right.
Columns or whatever.
In
that case, you wouldn't be able to.
Correct. That's right. So you're several pages ahead of us, but you're exactly right. That's exactly right. Yeah. Yep. It's a great observation. Yeah. Okay. So let me point to the summary of what's happened here. So remember, we in computing this matrix, we did so. We computed this matrix one column at a time. Differently, you can think of computing this matrix from a conjugation point of view. Change of basis point of view from where it was in the first place. So we already had that with respect to the standard basis. T was represented by the given matrix. We know that the change of basis is done by this conjugation here. Right, that's how that change of basis is done. This is a flashback to 5.3. We didn't use the word conjugation at the time, but this is how that change of basis goes. This matrix, change of basis from V to S, its columns are just the new basis. That basis, of course, consisted entirely of eigenvectors. Per our sort of, that was the idea, that was the theory of our attempt, is let's make these eigenvectors. And then so likewise, of course, these are eigenvectors. And then notice what's happened. These diagonal entries, where did those diagonal entries come from? Well, they ultimately they came from, I guess, here, which came from here, which came from eigenvalues. So these numbers on the diagonal, eigenvalues. And this pattern too is always going to hold when you can play this trick. Yes.
So does the S stand for the standard?
Yeah, basis? S for standard basis. That's right. Yeah. Okay. All right. So it's looking good. Seems like this ought to always work. Here's how we write it down as a proof. So I have a couple of things scratched off here. I'll reveal what's under the scratch outs in a few minutes, but for the moment, let's leave those scratched out. Let me zoom in on our theorem here. Here's the theorem. A matrix is diagonalizable. Yeah, let me do this better. A matrix is diagonalizable if and only if you can find a basis consisting entirely of eigenvectors. And this is if and only if. So these two statements are equivalent. If a matrix is diagonalizable, there is a basis of eigenvectors. And the other way, if you find a basis consisting entirely of eigenvectors, that matrix is diagonalizable. All right. This is actually a really straightforward proof. I just want to point out the first observation to make is that diagonalizability is exactly what this says. A is diagonalizable means that this matrix A can be conjugated by some invertible matrix. We'll worry about what those columns are later, but can be conjugated to make a diagonal matrix. That's the definition of diagonalizable. This bottom statement down here says, I will claim, this bottom statement says that there's a basis for Rn consisting entirely of eigenvectors. Now let's look at this bottom statement. What does this bottom statement say? Matrix times matrix is another matrix. Okay, sure, but remember you can do matrix multiplications one column at a time. So let's think, for example, about what does this product say about, this column multiplied by A gives you that column. Looking at the first column, this says that there's a vector V1, which when you multiply by A, gives a multiple of V1. That's an eigenvector, right? And likewise for all the other columns, as I have this. So this, this matrix equation I have down at the bottom, circled in green, that's a compact way to say that the vectors V1 through Vn are eigenvectors. Nevertheless, it is what that says. Okay, so if I want to prove that this is an if and only if, I want to prove this theorem, all I've got to do is write down some algebra between these statements. And the algebra is actually pretty straightforward. It's a couple of quick steps. First little bit, let's multiply that matrix over to the other side. No big deal, right? It's an invertible matrix by assumption. Next little bit of algebra is let's multiply that out. Think section 1.2. Think section 1.2. And let me zoom so we can see what's in there better. In section 1.2, we argued that when you multiply two matrices, you're talking about linear combinations of columns. If I take a linear combination of these columns here, where I use these numbers as my coefficients, well, those coefficients are mostly 0. I'm really just multiplying lambda 1 times V1. like that. Likewise for the other columns. Whoopsie, didn't mean to do that. Let's look at the last one. That last column, again, mostly zeros. There's a single non-zero entry in that yellow column. That lambda n gets multiplied by vn. That's it. So we get that. So, like I say, I mean, the algebra between these two statements is not that much, and thus this proof is pretty easy to do. Everybody on board? So, what I've left out, let me clean up my mess here. Okay, so so what we've concluded, looking at this statement down here in green, we've concluded that in this diagonalization, that matrix consists of eigenvectors. And specifically, let me just remind you that those are eigenvectors as part of a conjugation. Conjugations are always by a change of basis matrix. Okay. All right. Furthermore, you can see over here, these numbers are clearly the eigenvalues, those numbers there. Where did those numbers come from? Those are the diagonal entries. Those are the eigenvalues. Okay, so there you go. This is always going to play out this way when you can diagonalize. When you diagonalize a matrix, you're doing a conjugation. That conjugation's by a change of basis matrix. The columns are the eigenvectors, and the diagonal entries of the diagonal matrix are the eigenvalues. Okay. Quick pause. Questions? Everybody happy with this? This is a good one to stare at, by the way. Make sure you really digest. I mean, note that this statement here is literally just straight up the definition of diagonalizability, and this statement down here is just directly saying that those vectors are eigenvectors. So, I mean, this algebra between these two statements really is all that has to get showed here, which is nice. Okay. All right, now I want to give you a different point of view. This is perfectly sufficient. It's fine. No problem. The establishing of the truth of this theorem is done. It's fine, right? But proofs do have a second purpose. Establishing the truth of a statement. Yeah, right, absolutely. It's a big deal. Sometimes, though, what we like about a proof is that it gives a point of view, maybe a way of thinking about something that's useful. And so this next proof that I'm going to show you, it's not to fill in any gaps or the rigor of this proof. This proof here is fine. But I just want to give you a different point of view. So, again, I'm going to start with diagonalizability, and I'm going to try to get down to showing that there is a basis consisting of eigenvectors, but I'm going to do it in a different way. Here we go. A different point of view on diagonalizability. If you have a matrix that's diagonalizable, what that means is that there is a change of basis, same linear transformation, in other words, but with respect to a different basis, that linear transformation is diagonal. That, again, straight out of our first interpretation of diagonalizability. So, different starting point. The last proof started with thinking of diagonalizability from a point of view of conjugation. Here, we're thinking of diagonalizability from the point of view of change of basis. Okay. So, what can I do with this matrix? That's being as it is a diagonal matrix. And remember, we know a couple of nice facts about diagonal matrices. One of them is that the eigenvectors and eigenvalues are easy. Right? We made this observation before. So being a diagonal matrix, super easy to write down that the standard basis vectors are the eigenvectors and that the corresponding diagonal entries are the eigenvalues. We never quite proved that technically, but that's just to avoid sort of notational inconvenience. But we established this, I think, very comfortably. Everybody remember that fact? Okay. Now, here's where we're going to go with this. Y'all may recall that I put up a really detailed example last week at some point of different ways to look at the same numerical statements and realize that one is written in a certain language given a certain basis, and that if you identify the language, you can sort of interpret what it's saying and then translate into a different language. We're going to do exactly that here. So what I'm going to do is look at this statement here. I'm going to try to ask what language is being spoken here, interpret it accordingly, and then translate into a different language. Here's how that works. Reminder, D is that. This tells me what language I'm speaking. This tells me that this statement I have in blue here, this is a statement that's happening with respect to the script V basis. So, in fact, the fact that this is the script V basis tells me that these numbers, mostly zeros with a single one somewhere, those numbers represent coordinates with respect to the script V basis. Those numbers are describing a vector in script V language, you might say. What vector is that, right? So what vector has these coordinates with respect to that basis? And let me translate the question. What is this linear combination of those vectors? And the answer is VI. Right? If these coefficients up here, these coefficients are the ith standard basis vector, that one is in the ith position. Taking that linear combination of these vectors then gives us the ith vector in this list, which is VI. So these numbers, mostly zeros with a 1 in the ith position, that's in the spoken language of script V that clearly we're talking about. In script V language, that's just how you say VI. Everybody okay? Likewise, let's look at the other vector over here. So what's going on? What do these numbers here represent? Well, that's an output vector. That, therefore, is giving you coordinates with respect to that basis. Oh, how about that? It's again the script V basis. So these numbers represent the coordinates of something with respect to this basis. What linear combination? What do you get when you take this linear combination of those vectors? That's really the same question we had above. Again, VI. So the big idea then is, recognizing that this statement is in the language of script V, interpreting accordingly. That statement really is just saying T of VI equals lambda I VI. So you may recall, again, we did I made up an example with a bunch of context of, various bases, various coordinates, various vectors, blah, 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 a bunch of details. And we did this same kind of thing of identifying what's the language that's being spoken, translate accordingly, and infer what's really being said about the underlying abstractions. Okay, all right. So where do we go from this? My goal is to understand how this relates to the matrix A. The matrix A is in the language of the standard basis. So all of these things, if I want to translate into the language of the standard basis, T becomes A with respect to the standard basis. Everything else, these are just the vectors. I mean, when you talk about vectors in general with coordinates, you describe them with respect to the standard basis. So that's how we typically conceive of vectors. And so punchline, these vectors are eigenvectors. All of these vectors here are eigenvectors. So let me remind you from the very start of the proof here, we started by assuming that A was diagonalizable. From the diagonalizability, I've shown that there exists a basis consisting entirely of eigenvectors, which is what I wanted to show here. So same result, different point of view, pros and cons. The nice thing about this proof right here is it's pretty crisp and tight, and this doesn't require think about it in these different ways. It's a little bit more accessible, I think, and that's nice. It's crisper, right, which is good. This proof, a little bit weirder, right? But ultimately, I think there's something really powerful. I think there's a really powerful idea in the point of view taken in this proof, and that is to see that ultimately diagonalizability directly tells you about eigenvectors and eigenvalues. It just does it in the wrong language. But there's an immediate connection that you can see between diagonalizability and eigenvectors and eigenvalues. All you have to do is translate it accordingly. So anyway, there's something fundamentally really nice about that as well. I would encourage you to make sure you try to understand both of these proofs for their different benefits, right? Their different advantages. Both good. Okay, pause for questions. Any questions about any of this? All right, here we go. So kind of a summary here. Here's what diagonalizability looks like. Remember, diagonalizability means A is conjugate to a diagonal matrix. That can go either way. Either D is a conjugate of A, or A is a conjugate of D. Take your pick. These are, algebraically, these are equivalent, right? Don't forget that the purpose of a conjugation, you might say, or a point of view on a conjugation, is that this is how you do change of basis for linear transformations. So that matrix is a change of basis matrix. Literally, straight out of section 5.3, that is a change of basis matrix, right? And we saw in the last examples, I'll say in the last two proofs and in that initial numerical example, that the clever choice of basis to make this all work is a basis consisting of eigenvectors, and don't forget that that bottom basis shows up as the columns of the change of basis matrix. Okay, so this pattern is always going to hold, just as we saw in that example, that first example several pages back. All right, now a real quick observation I want to make. A lot of students look at these two equations and they kind of look, I almost said similar. They look, they have the forms are related, you might say, right? With one big difference, and that is that the negative 1 exponent is over there, kind of on the left side there, but it's over here on the right side there. And students sometimes get confused. Wait a minute, is it PAP or is it PAP inverse? Or is it P inverse AP? Which way does it go? It's really easy to get that backwards. You can memorize your way out of that problem, sort of. The shortcoming of memorizing your way out of that problem is that these are not the only two situations that you will find yourself in. For one thing, these are how you write them if P is, reasonably, conveniently chosen as change of basis from D to S. But what if, in the problem that you're looking at, for whatever reason, maybe you're not given P, maybe you're given Q, which is P inverse. Then it's going to be backwards, right? And you can go crazy trying to say, okay, well, the way it's supposed to be is like this, but then I've got to switch them because they wrote this thing backwards, so I've got to switch them backwards. And I don't know. I feel like that's fraught, right? There's a lot of opportunity for that to all you need is to make one mistake, and you've got it exactly backwards. Right? So let me show you how to resolve this problem once and for all without having to really memorize your way out of it at all. And that is, you know that these two matrices, by virtue of being similar, you know that they're conjugates of each other. So you know you're looking at something like this. You know that there's going to be a negative 1 exponent either there or there. Rather than memorizing it, instead, just write down what you know about these matrices. So what do I know about D? the diagonal matrix, the big thing that I know is that simply represents T with respect to the eigenbasis. That's the big idea. Diagonalization happens with respect to the basis of eigenvectors. Okay, what do I know about the original matrix A? Well, the A that was given presumably is given with respect to the standard basis. Let's say so in this case anyway. So that much you know. Let's write it in this way. Write it not in terms of the compact, don't fall for the, this is so compact and therefore convenient. No, it's compact and therefore the information is obscured, right? Flesh it out. All the giveaways are right there when you flesh this out, writing it as, linear transformations with respect to bases. And then everything kind of falls into place. So, specifically, the fact that is script V basis. Well, when you compose, when you multiply matrices, those have got to be the same bases. Because the language of what comes out of here has to be the same as the language of what goes in to here. Likewise, this basis has got to be the same as that basis. Oh, I forgot to, let me do it So those kind of have to pair up. Right? And then, analogously, the input language for what's on the left has to be the same as the input language for the product on the right. The output language from the left has to be the same as the output language for the product on the right. So those kind of have to pair up like this. And this lets you fill in exactly which bases go where. So this is got to be S. That's got to be S. That's got to be V, and that's got to be V. Just observing the bases. I mean, what's inside of A and what's inside of D, just, sort of pay attention to that, and you instantly know this right here. So at this point, it's a matter of just, being careful and identifying what you're looking for. If P is change of basis from V to S, then you know it's on the left. And therefore, this thing that's on the right, notice that's going backwards. That's not V to S, that's S to V. And therefore, the -1 goes there. Everybody see what's going on there? Yep.
Repeat the last statement for why the -1 for the last statement.
Yeah, so it's just a matter of, what do we know about, once we have these bases identified in this equation here, right? Then, what is this P matrix? P, let's take it as a given in this situation that P is change of basis from V to S. Well, there it is. So this thing on the left I know is change of basis from V to S. If I also know that P is change of basis from V to S, then that's P. So I can see it right there in the equation. And this I can see is exactly the opposite of P, and therefore that's P inverse. Yeah. Right. Okay, so please take this point of view, or at least please keep this in your stable of different possible ways of thinking about these things. If you want to sort of memorize just for sort of basic purposes, that keep these kind of on the tip of your tongue, I suppose that's fine. But when you have anything resembling a question, oh wait a minute, which way does it go? Oh, I'm only 80% sure I'm remembering that right. Do this. Okay, so here's our theorem. You can diagonalize if you can find a basis of eigenvectors. So let's look at this question. Can you find a basis of eigenvectors? How can I tell? Under what circumstances is there a basis of eigenvectors, and therefore under what circumstances can I diagonalize? So this goes to your question. Yeah, right. Roughly speaking, this is what it breaks down as. Let me remind you, we wrote down this a while ago when we were talking about eigenvectors, section 5.4. Right? For any given eigenvalue, the number of eigenvectors you're going to find is always less than or equal to the multiplicity. Right? Don't forget, we further made this observation that the multiplicities add up to n. right? So best case scenario, maximum total possible number of eigenvectors that you might find at most in. Our goal here is to find a basis for Rn of eigenvectors. A basis for Rn must have n vectors in it. So this, what we need to happen in order to get a basis for Rn consisting of eigenvectors, what I need is this best case. I need to have equality in all of these cases. For each eigenvalue, I need to find the maximum possible number of eigenvectors, namely the multiplicity. And if so much as even a single eigenvector, so much as a single eigenvalue, let's say, fails to give you the maximum possible number of eigenvectors, then we lose. We are not going to have enough eigenvectors. We couldn't possibly fill out an entire basis for Rn. We don't have n eigenvectors, and therefore it's not going to happen. The matrix simply will not be diagonalizable. Okay. Very quickly, I did gloss over a theorem here. There's, this down here addresses the count of how many eigenvectors. There is the further question of how do you know that those vectors will be independent. If you take a bunch of eigenvectors and you lump them all together into a single set, will they be independent? And the answer is yes. Proving this is a bunch of details that we don't really quite have time for in Math 216. You're welcome to take a look at the proof in the book, but you're not obligated to. So I'm just going to assert that's not a problem. Okay, so here's an example. Think back to our very first matrix where we found the eigenvectors and eigenvalues. Here's the characteristic polynomial. This first factor gives that eigenvalue and that multiplicity. So for this eigenvalue, we'd better find one eigenvector, and we did. Okay, for this second factor, we found this eigenvalue and multiplicity. So we'd better find one eigenvector, and we did. So this matrix is diagonalizable. In fact, we have diagonalized this matrix. This was our, when we did that first numeric example, start of class. This was the matrix we diagonalized, and notice, as predicted on the previous page, it took all of the eigenvectors that we found. For all of the eigenvalues, there were no missing eigenvectors, and we just barely had enough to make that work. Okay. Here's another example. We've studied this matrix previously. There's the characteristic polynomial. That characteristic polynomial has this eigenvalue and this multiplicity for that eigenvalue. That means that when, for that eigenvalue, we'd better find two eigenvectors if we want this to be diagonalizable. And we didn't. We found one eigenvector. That was it. Remember, we were sad about this because we were kind of expecting there to be two eigenvectors, but there was only one. And so one of the consequences we can now see, that matrix, and one of the things that's sad about that story of there not being the expected number of eigenvectors is we can't find a basis of eigenvectors. Therefore, that matrix is not diagonalizable. It just isn't. Too bad. So, there you go. Okay. All right. I want to show you some applications. I'm going to be pretty quick with these applications because these are not really the important applications. The big applications that I want you all to see are differential equations. We're going to solve a huge category of differential equations in Chapter 6, largely using diagonalizability. So it's that's really the big one. These are little, while we're here, we can go ahead and do these, and they're kind of convenient and cute, and they have their moments. But the big one is the differential equations. So very quickly, let me remind you, this matrix, we've diagonalized it. There it is. There's that diagonalization. You can see the original matrix. You can see the diagonal form, and you can see the conjugation. And you can see that that's a conjugation by a matrix whose columns are the eigenvectors, right? So this is the story we've established. Okay. All right, so suppose that you want to raise this matrix A to a high power. Let's just say throw it into a computer, right? Sure. Computers only have so much capability. They are way, way, way better at arithmetic than we are, but they are only so powerful, right? So, for example, if you want to raise this matrix to the power of 1 trillion, 100 trillion, something like that, right? The computer can't. That's not going to happen. That's too much. Right? Okay. So here's an idea. Here's how we can approach this. And it's a very clever idea. First, note that if D is a conjugate of A, then A is a conjugate of D. Then A squared is A times A. You know? And let's see here then. Well, now we're allowed to move parentheses around, right? That matrix algebra has this feature. Therefore, I can do that. The P inverse and the P cancel. And what I'm left with, you'll notice, is I have a copy of D. I have a copy of D right next to another copy of D, and that gives me D squared. So very nicely, because of this kind of telescoping, a power of A is a conjugate of a power of D. Just like A itself is a conjugate of D itself, so are the powers. And you can see this for higher powers. For example, if you had, let's suppose we were raising A to the third power, then I would have another factor of A over there, moving parentheses around. Those cancel. Those cancel. And note, then you would have D, D, D all right next to each other, and that would give you D cubed. So same deal for any power of A. And the nice punchline then is if you want to raise A to a high power, you look at this arithmetic over here. That's nasty arithmetic. Each time you want to raise to a higher power, you got to multiply by A again. So if N is 100 trillion, you've got a tremendous amount of calculations to do. And yes, there are clever moves that you can do to cut that down. It's still a lot of work. The alternative is to notice that instead you can raise D to a higher power, and that's effortless. You raise a diagonal matrix to a high power simply by raising the diagonal entries to that power. That's it. There's no sort of like linear combinations or dot products or it's you write it straight down. Right? Sure, then you do also have to do the conjugation thing, right? But that's 2 matrix multiplications. It's not 2 times 100 trillion. It's just 2. So that really is easy. Right? So very much easier to do this than it is to do that. Okay. The last example I'm going to show you. Let's see. Oh gosh, do we have time? Well, we have enough time to get started on this anyway. I want to talk about Fibonacci numbers a little bit. Hopefully, y'all have seen Fibonacci numbers previously. If you haven't, no sweat. It's a sequence of numbers that's defined by this relation. A Fibonacci number is the sum of the 2 previous. Right? Surprising instances where this shows up in nature and various applications, as it's kind of weird that this shows up as much as it does. The Wikipedia page for Fibonacci numbers is actually kind of fun with a lot of those applications. Anyway, here's what I'm going to do. I'm going to, instead of viewing Fibonacci numbers in relation, I'm going to view consecutive pairs of Fibonacci numbers as being involved in a relation. So that consecutive pair relates to that next consecutive pair, you might say, by multiplication by this matrix. And it's just an observation that that's what the first line of this equation does. The first line of this matrix multiplication just says Fn plus 1 equals Fn plus Fn minus 1. The second line just says Fn equals Fn. The second line doesn't really do anything in some sense. Okay, now, what's the point? What's the benefit of this? Yeah.
So where did you get that matrix?
Oh, I made it up. Yeah, this is clever observation, and I shouldn't take credit for it. Somebody showed me this trick But I just observed that this matrix in the first entry tells me that, right? And it's just a sort of observation that, hey, how about that? Sure enough, it just happens to represent all the information in the Fibonacci relation. Okay, I guess we are kind of out of time. That's too bad. We'll pick up here on Wednesday. See y'all later. Have a good day. Hang on just a second.